Hello everyone! Welcome to another week in the Python for Data Science course. This week is dedicated to NumPy, one of the most powerful and important libraries in Python for numerical computations. In this video, we will give a short introduction to the library and why to use it. We will talk generally about arrays and then introduce NumPy's array, the ND array. NumPy, without exaggeration, is the must-know Python library for numerical computation and data analysis-related applications. It is a very important, powerful, and for that reason, popular package. NumPy introduces us to array-oriented computing as the main structure in NumPy is the array. NumPy's objects are used extensively by many other computational and data science-related packages, and the module can be connected with libraries written in other languages such as C, C++, and Fortran. NumPy is often used with pandas as together they form a powerful toolbox for numerical computations and data analysis. In fact, a lot of the conventions and syntaxes we will learn this week can be applied to panda structures, as we will see in an upcoming week. NumPy is designed for efficient manipulation of large arrays of data. Allow me now to take a couple of moments to remind you in general terms what an array is. It is a structure for storing data, but the items stored in it are stored in a linear order next to each other in the block of memory. This mode can also be referred to with the term contiguously in literature. This is different from many structures we have seen so far, which, even though we perceive them as objects whose items are next to each other, for example in a list structure in Python, in memory, however, the elements are not necessarily stored next to each other. In an array, each item has at least one array index by which it can be identified, as is the case for most structures. Let's see some array examples. Here is an array also called an one-dimensional array because the data stored in it are organized along one single dimension. So we visually represent the structure and its content as horizontal table for the sake of explaining the structure. And here we highlight also the indices of the elements in it. So notice that again here, as we have seen in other structures in Python, indexing starts at 0, not at 1. So the first element's index or position is 0. Arrays can have more than one dimensions. Here we have a two-dimensional array, also known as matrix in some applications. The data here is organized along two axes, the rows and the columns. We can have many dimensions, but the visualization of an ND array for dimensions greater than 2 can end up being tricky. So why use the NumPy arrays and not the built-in structures we have already encountered in previous lessons? In our live lecture, I will give you a comprehensive comparison between the NumPy array and the built-in list structure, as it is commonly seen that the two are used interchangeably, wrongly, by some students or junior developers. But for now, let me tell you that NumPy arrays are significantly less memory intensive than the built-in Python sequences. Also, NumPy offers functions for performing complex operations on entire arrays in a vectorized manner, avoiding those loops. It has also been shown how NumPy is faster than code that uses regular Python structures and functions, and that is due to its C-based algorithms. It has in fact been shown that NumPy-based algorithms can be 10 to 100 times faster, sometimes even more, than their pure Python counterparts, and use less memory than those. In its simplicity, as we will witness this week, NumPy is very powerful. The ND array, the key feature of NumPy, which is basically the n-dimensional array object we will be using all week, is a fast and flexible structure for large data. There is no restriction about storing homogeneous data in an array, but I often find that makes more sense for real-life applications. So I would advise you, unless you really have to store only one data type in each array. We can perform various mathematical operations and other types of operations on arrays, as we will see. The syntax for those is not much different to the one we have seen and learned for scalar values in built-in Python objects. Let's get a first taste of NumPy in code. How can we create an array like this with NumPy in Python? First off, NumPy needs to be imported in our script. Most installations of Python, NumPy is included. For example, if you installed Python through the Conda environment as we showed at the beginning of this course, then NumPy should already be available for you to use in your system. If, however, you chose another installation and NumPy is not included, or for some reason you can't find NumPy and it gives you an error when you try to import it, you can then simply install it using conda install or pip install as we have seen. I will follow here the important convention of giving the library a short name. NP is commonly used for NumPy for calling its functions. To create this one-dimensional array we have here, we can simply type np.array and give as an argument inside the parenthesis a list with the elements we want to store in the array. We can assign this object to a variable. For example, I give it here to a variable called data. And here how it looks when we try to call it. We receive array and then the elements stored in it in the parentheses in a list type. You can also check the type of the data and see that it is actually a NumPy ND array. And you can also check its shape by typing the name of the array that you have given to it .shape. This gives the size of the array along each of its dimensions. Here we have one dimension, so you get only one value, which is 6, which is the length of the array. For two-dimensional arrays, we follow the same logic using a nested list this time, where each sublist corresponds to a row in the two-dimensional array. And here's what you get if you call data, which is the variable I have stored the two-dimensional array in. You can check that it is two-dimensional by checking its shape and verify. Here we get two values because we have two dimensions, and we also see that each dimension has a length of 2. You can also check the data type of the data stored in an array by typing the name of the array .dtype. And then we see the data type here is integer 64. We will talk more about the data types in NumPy in an upcoming video, so don't worry about understanding this for now. You can perform operations with ND arrays, either between an array and a scalar, as we do here. For example, we have an array called data, which is two-dimensional, here how it looks, and here we want to multiply this array with the scalar 10. What we get as a result is again an array where each element has been multiplied by 10. But we can also make operations, perform operations between two arrays. Here we just add data array to itself, and what we get as a result again is an array, a two-dimensional one, where each element in it is the element-wise addition of the elements in the two arrays that we are adding together. The way NumPy works on mathematical operations will be covered in the next video. For now, we underline that NumPy is a powerful package for numerical computation and other data analysis tasks, so it is really worth your time to get a good grasp of it. We can also use it with other tools, especially with pandas, as together they make a powerful toolbox for data analysis applications. NumPy has the ND array structure for array-oriented computation. Looking forward to talking more about ND arrays in the next video. See you there!